Did you know that the light you see from the sun isn't instant? It actually takes about 8 minutes and 20 seconds for sunlight to travel from the sun to Earth. That might sound like a long time, but it's because space is incredibly vast, and light, even though it's the fastest thing we know, still needs time to cover these enormous distances. This delay is a fundamental aspect of how we observe the universe. It means when we look at distant stars, we are actually seeing them as they were in the past. This simple fact opens up a whole universe of understanding about speed and distance on a cosmic scale, challenging our everyday perceptions. So, what is speed really? In simple terms, speed is a measure of how quickly an object covers a certain distance. Imagine you are walking to a friend's house. The distance is fixed, and the time it takes you to get there determines your walking speed. If you decide to run, you cover the same distance in less time, meaning your speed is higher. This basic concept applies to everything that moves, from a slowly crawling ant to a rapidly flying bird. We use units like miles per hour or kilometers per hour in our daily lives. But when we talk about the universe, these units become almost too small to be practical for the immense speeds and distances involved. The universe is mind-bogglingly big. Our solar system is just a tiny speck in our Milky Way galaxy, which itself is one of billions of galaxies. The distances between stars and galaxies are so large that using miles or kilometers would result in astronomically huge numbers that are hard to comprehend. Think about the closest star to our sun, Proxima Centauri. It's about 4.24 light-years away. This means light, the fastest thing there is, takes over 4 years to travel from there to here. This scale forces scientists to think about speed and distance in entirely new ways, leading to specialized units and concepts. To measure these cosmic speeds and distances, scientists use clever techniques. For nearby stars, they can use parallax, which is like how your finger seems to shift against the background when you close one eye and then the other. For more distant objects, they use standard candles, which are types of stars or supernovae with known brightness. By comparing how bright they appear to how bright they truly are, astronomers can calculate their distance. And by observing the redshift of light from receding galaxies, they can determine their speed. These methods, built on the foundation of understanding light, allow us to map out the universe and its dynamic nature. The fastest thing in the entire universe is light. Its speed in a vacuum, often represented by the letter c, is approximately 299,792 kilometers per second, or about 186,282 miles per second. This isn't just very fast, it's the absolute speed limit of the cosmos. Nothing with mass can reach this speed, let alone surpass it. This concept is a cornerstone of modern physics, as described by Albert Einstein in his theory of special relativity. It's a fundamental constant, meaning it's the same everywhere in the universe, for all observers, regardless of how fast they are moving. This universality is what makes it so important. Why is light the fastest? Einstein's theories provide the answer. He showed that as an object with mass accelerates closer and closer to the speed of light, its energy, and effectively its mass from an inertial perspective, increases dramatically. To actually reach the speed of light, an object with any starting mass would require an infinite amount of energy, which is simply impossible to achieve. Light itself is made up of particles called photons. Crucially, photons have zero mass. Because they are massless, they are not bound by this energy constraint and can, and do, travel at this ultimate cosmic speed from the moment they are created. Imagine a racetrack that circles the Earth. Light is so fast that it could zip around our planet more than 7 times in a single second. If you could somehow board a beam of light, your journey across countries and continents would be almost instantaneous. Compare this to the fastest jet planes, which take many hours to cross an ocean. The speed of light operates on a completely different scale of swiftness. It defines the boundary between what is possible and what is not in terms of motion and information transfer within our physical universe. This isn't just a suggestion, it's a hard limit set by the laws of nature. Photons, these tiny packets of light, are pure energy in motion. They don't need to speed up because they are always created traveling at light speed. Whether it's light from a distant star, the screen you're reading this on, or a simple flashlight, all these photons are zipping along at this incredible, constant velocity as long as they are in a vacuum. When light travels through a medium like air, water, or glass, it does slow down slightly, but its speed in a vacuum remains the ultimate benchmark. This unique property of photons, their lack of mass, is what grants them their status as the universe's speed champions. Let's put the speed of light into perspective by comparing it to other speeds we might be more familiar with. Consider the speed of sound. You've probably experienced the delay between seeing a flash of lightning and hearing the rumble of thunder. This happens because light travels almost 1,000,000 times faster than sound. Sound moves through air at about 343 meters per second, or roughly 767 miles per hour, depending on temperature and humidity. While this is fast for our everyday experiences, faster than a race car, it's incredibly slow when compared to the speed of light. That flash of lightning reaches your eyes almost instantly, while the sound takes several seconds to cover just a few miles. Now, let's think about the fastest things humans have ever built, like spacecraft. The Parker Solar Probe, for instance, is designed to get incredibly close to the sun, and has reached speeds of over 430,000 miles per hour. hour, about 692,000 kilometers per hour. That's astonishingly fast by human standards, fast enough to travel from New York to Los Angeles in under 20 seconds, yet this incredible speed is still less than 0.07% of the speed of light. So, even our most advanced technology moves at a snail's pace when compared to the cosmic speed limit set by light. It highlights the immense challenge of interstellar travel. Are there other things in the universe that move very fast, besides light itself? Yes, there are. For example, particles called cosmic rays, which are high-energy protons and atomic nuclei, can travel at speeds very close to the speed of light, perhaps 99.999% of CE. Similarly, particles ejected from powerful cosmic events like supernovae or active galactic nuclei can achieve tremendous velocities. However, it's crucial to remember that these particles all have mass, and therefore they can never actually reach 100% of the speed of light. They can get incredibly close, but they can never cross that ultimate threshold. The speed of light isn't just a record, it's a fundamental rule that governs how information and influence can travel through the universe. If something happens on one side of the galaxy, the effects of that event cannot reach the other side faster than light would take to make that journey. This has profound implications for causality, the relationship between cause and effect. It means there's a built-in delay in the universe, a maximum speed at which any signal, any force, or any object with mass can propagate. This ensures an orderly progression of events across the vast cosmic expanse. Understanding the speed of light is crucial because it helps us comprehend the sheer scale of the universe. When astronomers talk about distances in light years, they are using the speed of light as a measuring stick. A light year is the distance light travels in 1 year, about 9.46 trillion kilometers or 5.88 trillion miles. When we say a star is 100 light years away, it means the light we see from it tonight started its journey 100 years ago. This concept allows us to map out our cosmic neighborhood and beyond, providing a framework for understanding the immense distances that separate celestial objects. This finite speed of light also means that looking out into space is like looking back in time. The farther away we look, the further back in time we see. The light from the Andromeda Galaxy, our nearest major galactic neighbor, takes about 2.5 million years to reach us. So we see Andromeda not as it is today, but as it was 2.5 million years ago. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope are essentially time machines, allowing us to study the early universe, to see galaxies as they were forming billions of years in the past. This is only possible because light travels at a specific measurable speed. The speed of light as a universal constant is a pillar of Einstein's theory of relativity, which has revolutionized our understanding of space, time, gravity, and the universe itself. This speed limit influences everything from the behavior of black holes to the energy released in nuclear reactions, like those that power our sun. It dictates how GPS systems work with high precision, as they must account for relativistic effects. The fact that c is constant for all observers, no matter how they are moving, leads to mind-bending consequences like time dilation and length contraction, where time and space are not absolute but relative. Ultimately, comprehending the nature of speed, especially the speed of light, fuels our scientific curiosity and our quest to understand our place in the cosmos. It defines the boundaries of what's possible for communication and travel across interstellar distances. It shapes our most fundamental theories about how the universe works. By studying these cosmic speeds, we not only learn about the vastness of space and the arrow of time, but also about the intricate laws that govern reality itself. This knowledge is not just academic, it's a profound part of understanding the universe we inhabit and our connection to it.